Okay, today our last section, 2.9 of this chapter, is going to put two new types of variations out there for you to learn about called combined and joint variation. So when it says we're going to translate joint and combined variation language into formulas and then formulas back into their language, solve problems involving joint and combined variation, and then solve real-world problems. Now, what I want you to remember, here I'm going back to a slide we did the other day, is when we concluded the other day about having this last mass weight equals and what it depended on, we came up with an equation that looked like this. And I said in that lecture that we'd be talking about this later. We have three independent variables, one constant, k, and our dependent variable, m. So the maximum weight this board can hold depends upon our constant, and then the width of the board, the thickness of the board, and the distance or length of the board. So these three variables that are our independent variables are all in the same equation. Where earlier in the chapter we were just focusing on y equals kx or y equals kx squared if it was direct. Well, now we're going to open it wide open and say, well, we could have direct variables and inverse variables all in the same equation. So let's get to our definitions so you can understand which equations would represent which type of new variation equation. So with that, we have two new definitions, and double check. We have combined variation. Combined is when you have direct and inverse variations occur together in the same equation. A combined variation would be a perfect example of that scaffolding question from 2.8. You can have more than two variables, and so we had three independent variables and one dependent variable, and it could be numerous combinations depending upon the complexity of the situation. The other type, called joint variation, one quantity varies directly as the product of two or more variables, but not inversely. So we're talking about we can have two or more variables, but they all have to be in a direct situation. And we've been talking that if we see a direct, it's like a multiplying combination. So I'm just going to make one up here. If we had y varies directly as ab squared and the third power of c, we might have an equation that looks like this. It's all multiplication, they are all different variables, and they are combined in a situation. Now today you might see, I would suspect in your homework, some of the more complicated looking formulas, maybe formulas or that we haven't memorized before. Not that you're going to have to memorize them, but we're going to be manipulating these formulas. They're going to give you some values, real-world problems. If I give you words, you should be able to write it as the variables. If I give you the formula, you should be able to tell me how the relationships are using words. You should be able to go back and forth. So I think we are going to start that with a baseball problem. Pretty good since we got the playoffs going on right now. A baseball pitcher's earned run average, known as his ERA, varies directly as the number of earned runs allowed and inversely as the number of innings pitched. Write a general equation to model this situation. So you should be writing what you believe would be variables that could be appropriate. What powers do they need to be? You know, don't forget, since they're all variations, you got to have a constant in there somewhere. So go ahead, read that again, and write down your version of the formula. Give you a second to do that. Now as you're writing, do not forget you can have more than one variable. Okay, so if we go with it, and they didn't tell us variables like normally, I'm going to stick with trying to use variables that represent the situation. So in this one, if I would go with a baseball pitcher's earned run average, I'm not going to use ERA, but I am going to use the E, because ERA sort of looks like, might be three variables. So E, his earned run average varies. So there's my equal. Directly, I know I'm going to have a constant, so put that in. Now it's directly, so it's all multiplication at this point. Directly as the number of earned runs allowed. So I'm going to say R for earned runs allowed. And inversely, so I know division, as the number of innings pitched. So I'm going to put I for innings. Write a general equation to model the situation. That's what I have. Now, based on what you used, earned run average, whatever variable you used, has to equal your constant time, your earned runs allowed, and then divided by your innings pitched. Okay. That's how they could start. Write in a formula. No big deal. That might be all they ask. But then there might be others that give us a little more information. So let's take this one now. In a recent year, a pitcher had an ERA of 2.56, having given up 72 earned runs in 253 innings. So if you put that all together, I believe that's everything but K. Keep reading. How many earned runs would the pitcher have given up if he had pitched 300 innings, assuming that his ERA remained the same? So I believe if we take just that first complete sentence, so we're looking at, we're looking at in a recent year, the pitcher had, and highlight it, we're looking at, we got an ERA of 2.56. He had given up 72 earned runs and 253 innings. So if you look at that, I believe we can put those numbers in. So in your work, ERA, depending on where you set yours up, I'm actually going to go down here. 2.56 has to equal K times my R value was my earned runs. There were 72 of those. Divided by the innings pitched was 253. Now look carefully at that because that's going to allow us to give us our K value. We need the K value before we can go on and answer their final question about his ERA his ERA remain the same. How many earned runs would the pitcher have given up? So with this, let's go one step further and then I'll leave it to something you need to bring to class with you. This looks to me like a fraction, and so if you're looking at this as a fraction, we've got a 72 over 253. To get rid of that fraction, the best scenario would be to multiply both sides by the reciprocal. So we're going to go 253 divided by 72, and let me just highlight that in red as our step. So if we would do that same thing over here, our step would be 253 divided by 72. Okay. Everything will cancel on the right-hand side with the exception of our K value, and that's what we're looking for right now. Now go ahead and calculate. What do you have when you take that 253 times by that 2.56 and then go ahead and divide by that 72 innings. And I'm just going to double check mine. So if we round, let's say, to the nearest hundredth, we're looking at, if we round to the nearest hundredth, I'm looking at about a 9. If we don't, we've got a 8.9955555. So maybe let's go over nearest thousandths, and so we'll make that a 6. 8.996. And that would be the K value we would use. So then we could come back up here, put our K value in, 8.996. Look for our earned runs in that and look for our innings pitch. And I think you can find them both in the rest of that sentence, because the question is how many earned runs, so there's your unknown, would the pitcher have given up if he had pitched 300 innings, assuming his ERA remained the same. So according to that, how many earned runs? So right now, it is actually our value that we don't know. But put in the numbers you need for the other portions, and you should be able to solve this and bring that number with you to class, and we will check it to see how accurate you really were before we move on. Okay, I do believe we might be finished from there. And we are. So bring that number with you. We'll answer some questions. We'll maybe we'll do a little word to formula work when we come to class before we start working, but bring any questions you might have in regards to combined and joint variation equations. So if you also think there's 4 types of variations now: direct, inverse, combined, and joint. All 4 of them will be key as we move forward.